So at this point, we know how to address a memory position and write something in it. In this video, we're going to start understanding and taking control over exactly what we write there. In this code, I want to exploit the printf and write the hexadecimal value 41, 42, 43, 44 to the global integer num. We should easily see the value in it, given the last printf that prints the value in hexadecimal, so we don't have to debug it. These global variables are either stored in the BSS or data sections in memory. Given that this one is an initialized data, it will be stored in the BSS section, which address in memory is not randomized by default in GCC compilers in this Ubuntu 1632-bit system. If you want to have that, which would break this exploit we're going to write, GCC requires a specific position-independent execution, PIE or PI, flags to be provided in order to take full advantage of ASLR. As you can see, we just grabbed the memory address of num variable and will now start creating the Python payload to exploit this. Let's first figure out the direct parameter access index for an address placed at the beginning of our payload, such as these 4 A's. We can see it's at the 7th position, so if we do this, we should be able to write to that variable. There you go. The reason it prints 4 is because the payload has a 4-byte address in the beginning, before your %n. Let's now write a bigger number. Let's say A in hex, which is 10 in decimal. To do this, we could either manually insert the needed number of characters that would add up to 10 right before we wrote the %n, or we can simply use a minimum field width. Given that we want to store number 10 in decimal, we are going to have to subtract the 4 initial bytes, so we'll have 6 here. Let's now go for our initial objective, write 41, 42, 43, 44 in hex. Let's start with 41. 41 is 65 in decimal, so let's adjust it. However, that's bad coding, at least for exploit development. I don't want to be doing math to adjust a value in multiple lines. So let's rewrite this code. There you go. That's better. Let's add another byte and write 41, 42 in there. You can see how much easier it is now, instead of having to add or subtract values manually. Let's keep it up and write 41, 42, 43. You can see it takes a bit longer now, since 41, 42, 43 in decimal is over 4 million characters that the application is writing in the screen. However, keep in mind that in terms of the size of the character array where the string format is, it's actually quite small, since the rendering of all these characters is done while parsing through the format string inside printf's code. Now we're on to writing the 4th and last byte. As you might imagine, at this point, this step will simply take too long. If this is a remote exploit and you're doing a red team or whatever undercover op you're into, you don't want that kind of exposure going on for so long. Let's just jump forward in time and show this when it's done. As you can see here, it takes a few minutes to run, and that would ultimately be acceptable if it were our only option. But it's not. So how do we solve this problem? For example, with short writes. The word short here relates to short integer type, which is 16 bits or 2 bytes of length. And that's exactly what this writes, instead of the 4 bytes of %n. So how do you tell printf to write only 2 bytes? By using length modifiers. If instead of just using %n you use %hn, what you're telling printf is to write 2 bytes instead of 4. What this allows us to do is not take too long, as when we try to write those 4 bytes at the same time to memory. By the way, as you can see here, we can also write 1 byte at a time, but this will actually make our payload longer. So it's not necessarily the best solution, but we'll see that in a minute. Let's write some code to exploit this and write those 4 bytes, 41, 42, 43, 44, into that variable. we'll use struct to not have to reverse write because of little endian by hand every memory position, and have this struct back do that for us. The capital I will have it translate the address number to an exact 4-byte long value. In this code, we are doing 2 writes. The first will write the 4344 to position X, and the second will write 4142 to position X plus 2 bytes, because we're writing 2 bytes at a time with the length modifier. And that is all this code does, with a couple of tricks. Given that the first 4 bytes, as we've seen in the beginning, is accessed using the direct parameter access7, it's obvious that 8 will give us the second sequence of 4 bytes, which is why we place the second address there. Now, this line is pretty straightforward, as we've used the same technique in the previous iteration of this exploit, but this one not so much, more specifically because of this. What's happening here is a bit of a trick. Because we obviously want to write 4142, but this value is smaller than 4344, so the math will mess up the value we wanted to write in the higher 16 bits. To correct this, we add a 1 to the left of it, and what this does is result in a value that will end up adding just enough characters to our payload in order to complete a 14142 length of characters printed so far. The trick here is that printf, in using the length modifier h in %hn, will ignore any bits higher than the 2 bytes it wishes to write to the memory position. That way, what it actually writes is just the 4142 of the 14142 value, which is exactly what we wanted. But again, understandable code, but in these cases, you don't want to rewrite multiple lines while doing any sort of math whenever the addresses are different. So we'll write this instead. So what about writing byte by byte? I wrote such a code for you to see that it follows the exact same logic with some obvious differences, such as having the next memory address to write to 1 position after and not 2 as before, and having HHN instead of HN. So what's the difference? Why not do it this way all the time? This way is great if you want to write shellcode to memory and don't want to unnecessarily overwrite extra bytes in it. In some contexts, that could be an issue which forces you to use the HHN, but it also results in a longer injected string or character array. The payload for the byte per byte writing is much longer given the fact that you must place all the addresses referencing each byte in the beginning. And if you compare both codes we just wrote, you can see the first version, which writes 2 bytes at a time, is 32 bytes of characters long, whereas the byte per byte result is 60 bytes. You can imagine that if there were, for instance, a 40 character limit here, we wouldn't be able to use the byte per byte payload. Bottom line is, writing 1 byte at a time requires a longer payload, no such thing as 3 bytes at a time, and 4 bytes in one go takes too long to print out the printf. So 2 bytes at a time is usually how we go about it.